Linearity and nonlinearity play an extremely important role in mathematics, physics, technology, and in natural sciences generally speaking. All theoretically possible signaling processes, including the practically usable ones, can be distinguished by their linear and nonlinear properties. How do you find out if a process is linear or nonlinear when measuring it? If a sinusoidal signal of any frequency is entered into the input of a module, and if only a sinusoidal signal of the same frequency appears at the output, the process is linear. Otherwise, it is nonlinear. Let me now try and explain the terms linearity and nonlinearity in signaling processes in plain words, without using any mathematics. For the time being, flat and curved mirrors will suffice to provide an explanation. At least once a day in the morning, we look at our reflection in the flat mirror of our bathroom. In the mirror, we see a lifelike mirror image of our face. This is an example of a linear depiction caused by linear mirroring. Changing a signal by means of a signaling process can be described in a similar way. A characteristic curve, which plays a role of the well-known mirror, describes the relation between the input signal and the output signal of the component or the process. The illustration shows that the curve of the signal is projected vertically upwards onto the characteristic curve, and from there horizontally to the right. The projection is the equivalent of the mirroring process. A new signal is created by projecting a sinusoidal oscillation at a nonlinear characteristic curve. The sinusoidal oscillation contains merely one frequency, whereas a new signal contains several frequencies in the spectrum, bottom spectrum. If the characteristic curve is nonlinear, the proportions are distorted. The illustration shows a sinusoidal oscillation which is more and more transformed into an obtuse rectangular pulse. While the sinus contains just one frequency, the analysis of the obtuse rectangle shows that there are several frequencies. It follows from that nonlinear characteristic curves create distortions, which in the frequency range also create additional frequencies, which means nonlinear distortions. Now listen to the experiment. The situation is quite clear. There is just a total of 5 or 6 linear processes, and most of them appear ridiculously simple at first sight. But they are still enormously important and appear in numerous applications. In contrast to the indefinite variety and complexity of nonlinear processes, we know almost everything about them, and there are hardly any surprises, even when several linear processes are combined to form a linear system. The top series shows the original signal, filtered noise, in the time and frequency domains. In the center, the signal after amplification by 100, and finally at the bottom, the signal after damping by 100 multiplied by 0.01. It may come as a surprise that there are mostly extremely simply mathematical operations behind these processes, which, at first glance, have little to do with communications engineering. Addition and delay are other very simple linear processes. Strictly speaking, the Fourier principle can be seen as the addition of an infinite number of sinusoidal oscillations of different frequencies, amplitudes, and phases. Any signal can be seen as the addition of different sinusoidal oscillations. If a sine is fed into a longish cable and input and output signals are compared on the screen of a two-channel oscilloscope, the output signal appears phase displaced, that means delayed, compared with the input signal. To conclude the section on addition and delay, we should take another look at a particularly interesting and important special case: two successive delta pulses generated by delay and addition of one delta pulse. Each of the two pulses initially contains all frequencies of the same amplitude. The amplitude spectrum is thus a constant function. Accordingly, two pulses ought to contain all frequencies of twice the amplitude. No, they don't. The reason is that one of the delta pulses is delayed compared with the other one, and therefore has a different phase spectrum. As the illustration shows, the spectrum is sine-shaped. At the zero position of the spectrum, the sinusoidal oscillations of the same frequency and size are added in a counterphase way. That means they cancel each other out, and the result equals zero. This example is called a comb filter because equidistant frequencies are filtered out in a special way. All digital filters only contain the three processes: addition, delay, and multiplication with a constant value. This shows how important simple processes like addition and delay are in the field of analysis, synthesis, and processing of signals. Differential and integral calculus mean the beginning of higher mathematics. Both types of calculus are important because the most important natural laws and technological relationships can only be modeled by using the calculus. You should simply recognize by means of this illustration what differentiation as a technical signal process in the time domain actually means. Try to answer the following questions. At what points of time do local maxima and minima occur in the case of the blue differentiated output signal? What property does the red input signal have at these points of time? At what points of time is the differentiated signal equivalent to zero? What property does the input signal have at these points of time? In what way does the input signal differ at the places where the differentiated output signal has a positive local maximum and a negative local maximum equal to a local minimum? You should arrive at the following result. The differentiated output signal indicates how rapidly the input signal is changing. The process of differentiation can therefore also be used as a signaling device, whether something is changing too quickly or too slowly. Mostly it is used as a measurement device to show how quickly something is changing. Now we show the relationship between integration and differentiation. The appropriate experiment shows the agreement. The differentiation of the integrated signal produces the original signal. Thus, differentiation appears to be the reversal of integration. Differentiation can be seen as a reversal of integration, and integration means the reversal of differentiation. On closer examination of the signals, two further aspects in the time domain may be surmised. The integrated signal has far less edge steepness than the input signal. This would imply the suppression of higher frequencies in the frequency domain. That means a low-pass characteristic. The curve of the integrated signal looks as if the mean value were formed successively from the input signal. The curve decreases as soon as the input signal is negative, and increases once it is positive. We select a very straightforward signal curve in case of the periodic rectangular signal. This reveals a property of integration particularly clearly. Constant positive segments lead to a rising straight line, and constant negative segments lead to a falling straight line. Apparently, seen from a geometrical point of view, the integral successively measures the area between the curve of the signal and the horizontal time axis. The area of the first rectangular signal is 4 volts times 250 milliseconds equals 1 volt second. And it is precisely this value that the integration curve gives after 250 milliseconds. We must continue to differentiate between positive and negative areas, as the next area, in terms of the absolute value equally large, is deducted, so that after 500 milliseconds the value is again 0. The frequency domain on the right provides unambiguous qualitative and quantitative pointers. Initially, the integration quite clearly has a low-pass characteristic. In this case, a noise signal is integrated. The result is practically 0 with small fluctuations. At the bottom, we have a higher resolution. The process of integration adds up the positive and negative areas. Because everything is random in the case of a noise signal, there must be an equal distribution of positive and negative areas. On average, all areas must be zero. Accordingly, integration can be used to form the mean value, an extremely important aspect for measuring technology. In addition, forming a mean value apparently eliminates noise better than a normal filter could. Now we change to nonlinear processes. Theoretically, there is infinite diversity. Therefore, we have to be selective. At this point, we concentrate on a few fundamental processes. If necessary, others will be added, for instance in measuring technology. It is important to clarify the common features which nonlinear processes have in the frequency domain. What happens when two signals are multiplied with each other? Let us proceed systematically. As representative of all signals, we select two sinusoidal signals, both of the same frequency, amplitude, and phase size. You can see the astonishing result in the time and frequency domain. In the time domain, we see a sinusoidal signal of twice the frequency, which has a direct voltage superimposed on it. At the output, we find another frequency related to the input. By definition, this means nonlinearity. Now we study the multiplication of two sinusoidal signals of clearly different frequencies. In this case, the principle emerges clearly for the first time, which characterizes the frequency spectrum of most nonlinear processes: nonlinear linking of two signals. Literature talks of sum and difference frequencies, which means all the frequencies contained in this spectrum result from the sum and difference of all the frequencies contained in the two spectra of the input signals. The multiplication of a sinusoidal signal by itself can be used technically to double the frequency. The multiplication of two sinusoidal signals is obviously a nonlinear process, as the output signal contains different frequencies. The smaller one of the two frequencies determines the distance between the sum and difference frequencies. What other multiplication could be of technical importance? Intuitively, it would seem sensible to include the second most important signal, the delta pulse, in the multiplication. Sampling is always the first step of analog-digital conversion, ADC. From a mathematical point of view, the multiplication of a signal by a sequence of delta pulses. Using the example of a sinusoidal oscillation, the multiplication of a signal by a sequence of delta pulses is shown. The sequence of delta pulses has an infinite number of sinusoidal oscillations of the same amplitude, always at the same interval of 128 Hz. In the lower spectrum, you will only find the sum and difference frequencies of any two frequencies of the two upper spectra. Any signal process in the time domain is related to another process in the frequency domain. The multiplication process in the time domain with its sum and difference frequencies shows a special symmetry in the frequency domain. The symmetrical mirroring of the NF spectrum at every frequency of the delta pulse is called convolution. For every frequency of the sequence of delta pulses, there is therefore a sum and a difference frequency. The situation is presented even more clearly in the sampling of an SI function. As shown in Chapter 5, Symmetry Principle, the full bandwidth of the SI function, which are the originally positive and negative frequency regions, is convoluted at each frequency of the sequence of the periodic delta pulses. The spectrum of the sampled signal contains for an infinite number of times the frequency-related information on the original signal. Sampled signals, that means digital signals too, have always periodic spectra. Finally, we shall deal with quantization, an extremely important nonlinear process which always occurs in the conversion of analog into digital signals. An analog signal is continuous both in time and value. That means it has a certain value at a given point of time and passes through all intermediate values between its maximum and minimum value. A digital signal, on the other hand, is discrete in time and value. Before quantization, the signal is only regularly sampled at discrete points of time. Afterwards, this measurement is converted into a binary number. However, the stock of numbers is limited and is not infinitely large. A measuring instrument with 3 positions can only show 999 measurement values. This illustration shows a difference between these two signals. The analog signal is continuous in time and value. The sampled signal is discrete in time and continuous in value. And finally, the quantized signal. Accordingly, there is a difference between the original signal and the quantized signal. In the final analysis, there is a distortion of the signal. This difference is represented accurately in the middle. As the spectrum of the difference shows, it is a kind of noise, which is called quantization noise. In order to keep this difference as small as possible, so that this quantization noise is inaudible, the step curve must be made smaller until there is no visible or audible difference between the two signals, as for example in hi-fi technology.